or conventional, actually conventional equation, the HCl. HCl is really ionized. So once we get the white precipitate, we can do some additional confirmation tests. And so we might stop here and say, okay, this test's positive for silver ion. But what we're going to do in this particular instance is we're going to take that precipitate here and then dissolve it in ammonia. So we'll take our silver chloride solid with 2 ammonias, and what that's going to do is it's going to dissolve the precipitate with this driving force of forming the diamine silver ion. This diamine silver ion turns out to be quite stable, and then we'll have the chloride out here. So that's that step. So what we're going to do is we're going to take our white precipitate and then dissolve it in ammonia to form the diamine silver ion, silver 1 ion. And then what we're going to do is we're going to reprecipitate it out with nitric acid. And so one way of thinking about this is just removing the ammonia using nitric acid here. In other words, we're going to have the ammonia react with the H+. We could use any acid for this, except hydrochloric acid wouldn't be good. I mean, because it would provide chloride for the silver ions. We have to have the chloride already present to form ammonium. So removing the ammonia from this equilibrium will just shift it to the left and reprecipitate out our silver chloride. So here this is positive for the silver ion. Okay, once we're done with that, then this is the end of the line for the silver chloride. We can dump that in the waste container. We're going to continue on with the supernatant. Now the other ions didn't, the remaining cations did not react. And so, for example, iron 3+, etc. These, when we react this with HCl, we get NR. So the only thing that reacts with HCl is silver ions here. The remaining cations go over here. Now, this is very tricky here, because what we want to do is we want to precipitate out the 3+ cations here. Iron 3, chromium 3, and aluminum. If we just add ammonia alone, what would happen is if we add just ammonia alone, what would happen is we'd precipitate out the iron 3, the aluminum, and the chromium 3 like we want. We want these as hydroxide, so we want the iron 3 hydroxide, chromium 3, and aluminum hydroxide. And ammonia will supply enough hydroxide to do this, because ammonia is a weak base. Weak bases hydrolyze water to produce hydroxide. And the amount of hydroxide is very small, but it's big enough to precipitate these out. But it's also big enough to precipitate out magnesium, nickel, and zinc. These also form insoluble hydroxides. And so we're in a tricky place here, because we need enough hydroxide to precipitate out these, but not too much hydroxide. If we have too much hydroxide, we're going to precipitate magnesium, nickel, and zinc. Those also are insoluble hydroxides. So what we're going to do is we're going to make a buffer. And so we're going to add 2 drops of ammonium and then just raise the pH. Here we'll want to use litmus paper, to get it, to make sure it's basic. And so ammonium's an acid, HCl's an acid. How much ammonia we have to add depends on how much excess HCl we put in there. If we have a lot of HCl, then we're going to need a lot of ammonia to do that. And the HCl reacts with ammonia to make ammonium. And ammonium is also acidic, so we'll have to just keep adding ammonia until it turns red litmus blue. We may want to add a little bit more because we want to make sure we have enough precipitate here to analyze, but we got to be careful because adding too much ammonia can result in precipitation of these +2 cations. Does that make sense? Here. And so here we probably should use litmus. For the other steps we don't need litmus. All right, so we're going to get a mix of precipitates, rust, gray, green, and colorless, corresponding to these. And these aren't very dense precipitates. These precipitates don't really sink to the bottom. These are very low density. Some people refer to these as cottony, wispy precipitates, or gelatinous precipitates. And so these form gelatinous precipitates. Aluminum hydroxide is almost invisible. And so what we're going to do is we're going to separate these precipitates by trying. But first we got to wash the precipitates. We wash it, and then the first rinsing goes with a decantate. The second, and if you do a third rinsing, discard, so that we have clean precipitate. And then to this clean precipitate we're going to add sodium hydroxide. Well, sodium hydroxide, unlike ammonia, supplies a lot of hydroxide. Ammonia, is a weak base. Sodium hydroxide is a strong base. That's going to supply a lot of hydroxide. Well, that's okay because we've already separated out the +2. If we added the sodium hydroxide earlier, we would have precipitated out the zinc, the nickel, and the magnesium. But since we're just adding it to this, then it's okay. But what's the purpose of the hydroxide? Because we already have the hydroxide precipitates. The purpose is, and you probably didn't know this, is the purpose is to separate out the aluminum. And so, here, it seems to be working. So when we look at the, when we look at the aluminum hydroxide here, we're forming the aluminum hydroxide. And if we add excess hydroxide, like one extra hydroxide, what happens is this precipitate disappears. And we end up with the, how would you name this? We'd name this tetrahydroxido aluminate 3 ion. And so we end up with a complex. This is a Lewis acid-base reaction in which we're forming this stable complex. Interestingly enough, we do not form a tetrahydroxido ferrate nor tetrahydroxido chromate equivalent. It's just the aluminum that does this. Now, how do you know that? How could you have predicted that? The way we predict this is empirically, just by experimental evidence. It just didn't happen for these. It happens for aluminum. And so this gives us a way to separate out the aluminum. But what about the chromium? How are we going to separate out the chromium here? Then the way we're going to separate out the chromium is by oxidizing it. And so what we're going to have here is we're going to have the chromium 3 hydroxide solid, and we're going to oxidize this with hydrogen peroxide. When we oxidize this with hydrogen peroxide, we're going to form the chromate ion. And so this is what we call skeleton redox here. And what we're going to do is we're going to balance this skeleton redox down below. And so C below. I need some more room to do this. So we're taking our chromium 3 hydroxide, and hydrogen peroxide, and we're going to convert the chromium 3 into chromium 6. And so we need to separate this into 2 half reactions. The 2 half reactions would be chromium 3 hydroxide solid goes to chromate. And the other half reaction is hydrogen peroxide goes to blank. Alright, so we'll just use the techniques from chapter 5 to balance this. We have one chromium, so the chromiums are balanced. And then we have 3 oxygens and 4 oxygens over here, so we'll need 1 water. That'll give us 4 oxygens and 4 oxygens. Then we have 2 plus 3 is 5 hydrogens over here, so we'll need 5 H pluses over here. And then we look at the charge. It's neutral on the left. On the right, it's -2 plus 5 is +3. And so we'll need 3 electrons to balance it. So we're going to convert chromium 3 to chromium 6 by losing 3 electrons here. All right, for the hydrogen peroxide, we have 2 oxygens over here. And so what we're going to need is we're going to need 2 waters here to balance that out. That's going to give me 4 hydrogens on the right, 2 hydrogens on the left, so I'll need 2 H pluses on the left. And then the charge, I have neutral on the right, and I have +2 on the left, so I'll need 2 electrons for this. All right, then I have 3 electrons here, 2 electrons here, so I'm going to multiply the top one here by 3 and the bottom one here by 2. And then I'm going to combine these 2 half reactions. So that's going to give me 6 electrons here, and then 2 times 3 gives me 6 electrons here, so the electrons cancel. And then I'm going to have 3 times 2 is 6H plus, but down here I'm going to have 10H plus. And so on the right side I have 6 and then I have 10, so I'm going to end up with 4 H pluses net on the right side. Takes care of the H pluses. Then I'm going to have 3 hydrogen peroxides on the left, so I'll write those here. And then over on the right I'm going to have 3 waters here and 6 waters here. And so the waters cancel out on the left, and that leaves me with 3 waters on the right. And then I'm going to have the chromium 3 hydroxide. We'll put that here. Okay, and then over here I got the waters already taken care of. This is going to form chromate. And then the H pluses, I already took care of those. And so this is it. So this should be the balanced redox reaction. Let's double check that it is balanced. I'm going to double check by atom and charge balance. So 6 hydrogens plus 3 hydrogens is 9 hydrogens. 4 hydrogens plus 6 hydrogens is 10 hydrogens. Somehow I didn't balance it correctly. So that's 6 and 9. I mean 6 and 3. 6 and 3 is 9. 4 and 6 is 10. So I screwed it up. And so let me go back and see where I screwed it up here. Let me just check the half reactions, make sure they're balanced. So I have 2 plus 2 is 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygens, charge -2 plus 2, 0 and 0. So this one's balanced. Let me check this one to make sure it's balanced. So 2 hydrogens plus 3 hydrogens, 5 hydrogens, 5 hydrogens. 1 plus 3 is 4 oxygens, 4 oxygens. Charge is neutral, -2, -5, plus 5. This is balanced too, so I must have screwed up on the addition here.
Two chromium hydroxides on the left.
2, oh yeah, 2. I forgot to multiply that through, shoot.
And 4 waters.
And 4 waters, all right. All right, so now let's double check, thanks. So that's 6 plus 6 is 12, 4 plus 8 is 12. 6 oxygens plus 6 is 12 oxygens, 4 plus 4, I need 2 chromates here. That gives me 12. 2 chromiums, 2 chromiums, and this is balanced. Okay, let's check the charge. +4, -4 is 0. So this looks good. Yeah. All right, it turns out that hydrogen peroxide is our oxidizer that's taking electrons. And chromium-3 hydroxide, that's our reducer. Going forward, in the reverse direction, what takes electrons? The chromate and the H plus take electrons. So chromate and H plus, that's my oxidizer. And what's my reducer? The reducer is water here. And that would be the reducer. So we're going from stronger to weaker. That's the driving force. So this would be the redox reaction here. So what we're going to do is we're going to oxidize the chromium-3 hydroxide and convert it to chromate. Chromate is a yellow solution here. And that's going to leave the iron. We can't oxidize the iron. The iron's already 3+, and that's kind of where it stops. And so the iron 3+ is not going to be affected by the hydrogen peroxide, nor will the aluminum. The aluminum at 3+ is already maxed out as well. Okay, then we wash, decant, wash the precipitate, combine, decantate, wash, clean. Then we got the clean iron 3 hydroxide. This is a gelatinous precipitate. It's yellow, rust-colored precipitate. Then we'll dissolve that precipitate. And so we're going to take our iron 3 hydroxide and dissolve it with HCl. The chloride does nothing here, so we're going to need the H+, and that's going to form Fe3+ plus 3 waters. So the driving force for this is just a metathesis reaction and formation of weaker acid, in this case water. And then we end up with Fe3+. Fe3+ is going to be a yellow solution, but it might be very faint. It might be hard to see the yellow color. And so what we're going to do is we're going to precipitate it out. And the anion we're going to use is this. Do you know what this anion's called here? It's a complex anion. It's called
hexacyanoferrate?
Yeah, hexacyanidoferrate or hexacyanoferrate, either one. What's the charge on iron? Is it 3+ or 2+? 2+. So this would be hexacyanidoferrate 2. So this compound is called potassium hexacyanoferrate 2. Well, we're going to just do a double replacement or metathesis reaction. So what we're going to take is we're going to take 4 iron 3 pluses and 3 hexacyanoferrate 2s, hexas. This is 4 minus, and then form this precipitate. This precipitate is going to be Fe4 and then 3 of the hexacyanoferrate 2 ions, and it'll be solid. This is the blue precipitate here. This is called Prussian blue. It's a famous precipitate. Prussian blue is what they use, I think, in blue jeans, in dyeing blue jeans. So it's a dye. All right. So that's positive test for iron. Then we're done with that blue precipitate. Over here, we're going to analyze this solution, which is going to contain the tetrahydroxidoaluminate 3 and the chromate ion. Okay, what we need to do is we need to remove the hydrogen peroxide. Hydrogen peroxide is an oxidizer. It's probably not strong enough to oxidize chloride. Chloride's hard to oxidize, but it probably is strong enough to oxidize ammonia. So we don't want to oxidize ammonia. Ammonia is electron rich, and so we need to remove the hydrogen peroxide so it doesn't react with the ammonia to make toxic oxides of nitrogen. So we'll just heat it. Just heat it. If you get it to, let's say, boiling, stop. You don't want to heat it to dryness, but if you get it heated to boiling, that's probably enough to decompose the hydrogen peroxide. Hydrogen peroxide decomposes into water and oxygen. Okay, then we're adding HCl. The HCl is going to kill the complex. And so if we have the tetrahydroxyaluminate ion, we can add 4 H pluses. The H pluses will react with the hydroxide ligands and convert those into water. So this is like an acid base or Bronsted acid base, or like kind of a metathesis sort of reaction here. And then the acid converts chromate into dichromate. So let's take a look at the conversion of chromate into dichromate. To make dichromate, you need 2 chromates. But dichromate is a bit odd because 2 chromates would be Cr2O8, but dichromate is Cr2O7, 2 minus. And the reason for this is this. Do you know what kind of bond this is?
Peroxide.
This is a peroxide bond, and are peroxide bonds very stable? No, they're not stable. And so what we want to do is we don't want peroxide to form. We want this. This is called a bridging oxygen. And so bridging oxygens can bridge like 2 hydrogens. That would be water. Or it can bridge a carbon and a hydrogen. That would be an alcohol, etc. So bridging oxygen is not a problem. So what we need to do is we need to remove one of these oxygens. But where does that oxygen go? If we remove one of the oxygens, where does it go? Is it stable as just a single oxygen atom? No, it's not. Probably the best thing to do is to combine it with hydrogen. If I can combine it with hydrogen, I can form H2O. And so that's probably the best. And so what I'm going to do is I'm going to take 2 H pluses and 2 chromates to form a dichromate and water. And so the oxide has some place to go, and the oxide is going to combine with the H pluses to form water. Does that make sense? And so we get rid of one of the oxygens. And so this is going to convert chromate into dichromate. This is a Lewis acid-base reaction. Yes.
Would the dichromate be more stable and so favored in this reaction?
Yeah, a dichromate is favored in acid, but oddly enough, chromate's favored in base. And so you can tell because chromate is yellow, dichromate is orange. And so you can switch it between yellow and orange just by adding acid or adding base, changing the pH. And so the stability depends on the pH. Well, anyway, we're converting our orange. We go from yellow to orange and then back to yellow. We're going to go back to yellow because we're adding base now, ammonia. And the base is going to attack the acid here. When the base attacks the acid, it shifts the equilibrium back to yellow. Here. Okay, so when we add ammonia, what's present? Well, we're going to have aluminum ions and dichromate. The dichromate goes back to chromate. The aluminum, however, is going to precipitate out as a hydroxide. So here we're not going to bother buffering it. Over here we buffered it. It was ammonia plus ammonium. The reason we buffered it with ammonium is to prevent precipitation of the +2 cations. Here, there are no +2 cations to precipitate, so we don't need to buffer it. We can just add ammonia to maximize the amount of hydroxide we form here. And so we try to get as much hydroxide as possible. And so the reaction there is this. It's going to just be aluminum 3 plus 3 ammonias plus 3 waters. 3 ammonias plus 3 waters will make 3 ammonium hydroxides or 3 hydroxides to precipitate out the aluminum solid plus 3 ammoniums here. So we get the aluminum hydroxide precipitate. Now this aluminum hydroxide precipitate is difficult to see because it's colorless. And so what you'll do is you just keep adding the ammonia to try to maximize this precipitate. We don't have to worry about amine complexes forming. If we did, then we got to worry about not adding too much. But here it's okay. This precipitate's really hard to see. And so what we're going to do is we're going to color the precipitate with a dye. In order to color it with a dye, we're going to first redissolve the precipitate. And so we're going to take the precipitate that we just formed and dissolve it again with acid. And so 3H plus is here. This is going to form Al3 plus 3 waters. And then we're going to add aluminon. Aluminon is the dye. And then we're going to reprecipitate it by adding ammonia again. So here we're going to take our Al3 plus and reprecipitate it by adding ammonia. But what's going to happen is this dye is going to get incorporated into the crystal structure. And we see that in other cases. For example, do you know what rubies are made out of? Rubies are made out of aluminum oxide that's been contaminated with a little bit of, I think, chromium. It gives it a little color to it. This is colorless, and so it's kind of like a dye. Rubies are dyed aluminum oxide. Well, we're going to have aluminum hydroxide, but it's going to be dyed red. And so what I'm going to do is I'm going to put a little double dagger there and call this a solid precipitate. This is my red precipitate. Now this red precipitate, what we're going to do is we're going to centrifuge it, because the red precipitate is suspended like this, and it's gelatinous, so it's wispy, cottony precipitate. And after centrifuging this, the precipitate is going to be forced to the bottom of the test tube. But the precipitate looks funny. The precipitate is like jello. And so what we're going to form is a red jello layer. And it's solid. It doesn't look solid, but it is solid. And so red solid jello at the bottom. And above this we'll have our liquid here. This jello layer is what they call a red lake. It kind of looks like a red lake that's at the bottom of the test tube. But it's not a lake, it's just a layer of red jello precipitate at the bottom. And so that's our red lake. So red lake is a positive test for aluminum ion. Then we're going to the chromate. Okay, so what we need to do is we need to separate out the aluminum hydroxide precipitate, wash it. First washing will go with the decantate here. Now the chromate, what we're going to do is we're just going to do a simple precipitation, that is a metathesis. So barium ions like chromate, and we form a precipitate. So the yellow chromate, this is going to result in a yellow precipitate. And so this would be our yellow precipitate. They say pale, but it's not so pale. It's fairly bright yellow. The solution is also yellow, so you have to be careful. We're talking about a yellow solid, not a yellow solution. All right, so that's the analysis here. Now, what about the decantate from earlier? The decantate from earlier has a +2 cations here. So what we're going to do is we're going to analyze those. The first thing we're going to do is we're going to add ammonium oxalate. And ammonium oxalate only precipitates out with the calcium. So calcium plus oxalate gives us a white PPT of calcium oxalate. Magnesium and zinc don't precipitate under these conditions. And so we're going to take a white calcium oxalate precipitate and then dissolve it in acid. So if we dissolve that in acid, this is just a double replacement or acid-base reaction. We'll need 2H+, and that's going to form calcium ions and oxalic acid, H2C2O4. Driving force for this would be stronger acid H+ to weaker oxalic acid. And that gives us calcium ions here. Now, we have the calcium ions here. We're going to do the red flame test. Now, in here we have the platinum wire, which we're going to use for the flame test. So what we do is we dip the wire into the solution and then just put it in the flame. And it should color the flame red. But the problem is these platinum wires are quite dirty. And so we have to clean them first. So if I grab one of these, this one has a lot of black residue on there. And so the way we clean it is we just burn off the residue. You burn it off inside the hood. But do you know it's going to take a long time to burn this off? Like 3 hours or something like that. We don't have that much time. So we're going to try to speed this up. One way to speed this up is we're going to get some concentrated hydrochloric acid into the test tube and then dip our wire into the concentrated hydrochloric acid and burn that. And hopefully that helps break things up. There are a couple of things. One, concentrated hydrochloric acid is very corrosive, and it has a powerful odor. And so you don't want to smell it. And so don't hold the test tube under your mouth or nose. You're going to get a whiff of HCl gas. So it has do this in the hood. You don't want to be cleaning this with concentrated hydrochloric acid on the bench and breathing in the vapors. All right. The second thing is we have to worry about thermal shock. That is, if you heat this to glowing and the glass gets hot and then you dip this in here, if the hot glass touches the concentrated hydrochloric acid, then it's going to contract rapidly and fracture it. And so we'll get mechanical fracture from quenching this. The other thing that can happen with glasses have an amorphous structure. And what can happen is this amorphous structure can crystallize. That is, it's called devitrification of glass. When we have devitrification of glass, it loses this kind of mechanical strength here because if we form some kind of salt crystal, they're kind of brittle. And so a lot of these ionic crystals are brittle and fracture, and so the glass will start to fracture due to devitrification. Things that promote devitrification are ions. And so it could devitrify by hitting a solution with ions in there. Anyway, this is a bit of a pain to clean, so we only want to clean it once. Therefore, I didn't want you to do the sodium test yet. What we're going to do is first clean this with the concentrated HCl and then heating it in the flame until there's no color imparted to the flame. We want this to be just the flame color, basically. Then we're going to test it with the calcium solution. So dip this in the calcium solution, put it in the flame, see if it turns the flame red. If it turns the flame red, then we're good. The red, it doesn't take long to burn off. It takes less than a minute to burn the red off, usually. Depends on how concentrated it is. Once all the red burns off, then the flame, there's no color imparted to the flame. Then we're going to test our original solution for sodium ions. Sodium gives a very intense yellow color. But we got to watch out because your original known solution contains chromium, nickel, zinc. We don't want to breathe those in either, so we're going to test those inside the hood. So we'll test for sodium inside the hood. And some of these, chromium imparts a color to the flame, but sodium's so intense it drowns out that color. You have to be very careful with sodium because sodium is the one ion that has the most false positives. There are a lot of students who say they tested positive for sodium, but it turned out to be contamination. yes, they tested positive for sodium, but there was no sodium in their unknown. It's so easy to contaminate anything with sodium because everything you touch, you leave a residue of sodium ions. And the residue is strong enough to give a solid yellow color to the flame. And so what you need to do here is take a look. If it's a very faint yellow color, that could be due to contamination. The concentration of our known solution is fairly high. And so you should see a very bright yellow color. So faint yellow color, I'd start to worry about contamination because sodium is hypersensitive. It gives a very, very intense color at low concentration. So if it's very faint, it's probably trace concentrations due to contamination. All right, once you test for sodium, it's either going to count, positive or negative, and then we're done. We don't have to clean this anymore. All right. Let's continue on with the other branch here. So we have the remaining cations in the decantate here. And then we're going to evaporate to remove the ammonium ions. Here. Ammonium is an acid, and we're adding sodium hydroxide. So we don't want to overdo it with the amount of sodium hydroxide we add. So we're going to try to drive off ammonium as ammonia, probably. And then add the sodium hydroxide. Now, the odd thing about sodium hydroxide is hydroxide, as far as ranking goes, the most hydroxide we're going to get is from sodium hydroxide. And then ammonia. And then the least amount of hydroxide we're going to get is from the ammonia-ammonium buffer. So here we're going to have increasing hydroxide concentration. So now we're going to add sodium hydroxide. We want a high concentration of hydroxide because nickel, it's no problem. High concentration of hydroxide will just precipitate out more green precipitate. But for zinc, it's a problem. And so when we add sodium hydroxide, it depends on how much we add. And so magnesium, it's no problem as well. So we're going to have magnesium plus 2 hydroxides. That's going to yield white magnesium hydroxide. Nickel plus hydroxide yields nickel hydroxide precipitate. And zinc plus hydroxide, 2 hydroxides, yields zinc hydroxide, which is white. Now, if we take these 3 hydroxides here and then add excess hydroxide, then nothing happens to the magnesium. So magnesium hydroxide, Nr. So it just stays. Nickel hydroxide, Nr. However, zinc will form the tetrahydroxidozincate 2 ion. And so adding excess hydroxide will dissolve the zinc. So initially we'll get a white precipitate. That white precipitate dissolves. But it's very hard to see because magnesium hydroxide is also white. And so if we have both zinc hydroxide and magnesium hydroxide, we don't know. It's hard to see. And so we got to make sure that we're adding enough hydroxide that we don't see any change in the amount of white precipitate. Now if you have green and white precipitate, it makes it even harder. But the easiest is just to add excess. There's no problem here. We want excess hydroxide. So. Okay, then we wash the precipitate, combine the decantate, wash again. So now we have a clean mixture of magnesium hydroxide and nickel 2 hydroxide. And the way we're going to separate these 2 hydroxides is we're going to take advantage of another complex. So we took advantage of the hydroxido complex. Now we're going to take advantage of the amine complex. Because when I add ammonia, ammonia supplies hydroxide, but it's also a ligand. And so when I take magnesium hydroxide and try to attack it with the amine ligand, nothing happens. No reaction, because it's already a hydroxide. And it doesn't form any complexes. However, when I take the nickel hydroxide and add ammonia, in fact, I'm going to need to add 6 ammonias here, at least. that's going to form this. NiNH3, 6. What's the charge on this complex?
2 plus?
Yeah, 2 plus. Or is it 2 plus? It's 4. 6. Yeah. 6. Yeah, it's 2 plus, so this is wrong. This says 2 minus, it's 2 plus. It's probably just because the photocopy was so bad. Which is a pale violet complex, the hexamine nickel 2 ion. The magnesium hydroxide stays over here. We wash the magnesium hydroxide precipitate, combine the decantate, and wash again, discard. Okay, then what we're going to do with the magnesium hydroxide precipitate is we're going to dissolve it in HCl. So magnesium hydroxide, we'll need 2 H plus, and this is going to form magnesium ions in 2 waters. So we dissolve the precipitate, and then what we're going to do here is we're going to reprecipitate it with the dye. So we're going to take our magnesium ions here, and then add the magnesium reagent, and then add sodium hydroxide. So we'll need 2 hydroxides for this, and the dye, which we call the magnesium reagent here. This is the dye. And then we're going to form a colored precipitate in which the dye complexes with some of the magnesiums. We don't need a lot of dye. But this is a blue precipitate, and it's gelatinous. With these gelatinous precipitates, we can centrifuge to make a jello layer at the bottom. That jello layer looks like a lake. So we'll take our blue precipitate, which is kind of gelatinous and floating all over the place, and then we're going to centrifuge this to compact it to the bottom, but it's kind of weird how it cakes on the bottom as a gelatin layer here. And this gelatin layer here is our blue lake. After centrifuging it. And so if we get the blue lake that's positive for magnesium, here, the blue lake. All right, then we have our hexamine nickel complex. In the hexamine nickel complex, we're going to add DMG, dimethylglycine, to that. And so we'll take our hexamine nickel complex and then add DMG. All right, we're going to add 2 of these. And then we're going to form this red precipitate. So the reaction for this is the DMG is kind of a weird organic ion. It's C4H7N2O2, and it has a minus charge. And the red precipitate is just going to be this stuff here, Ni with 2 of these ions stuck on it. So that red precipitate is positive test for nickel. Okay, then we go back up and take a look at what happened to zinc. The zinc we separated out as a tetrahydroxido zincate 2 ion. And to this tetrahydroxido zincate 2, we're going to add HCl and then precipitate it. And so here we'll take our zinc hydroxide plus 2H plus. This is solid. This is going to produce Zn2 plus 2 waters. Okay, then we're going to take our Zn2 plus and use this, the hexacyanodoferrate 2 that we used earlier. But rather than precipitating did we precipitate earlier? Rather than precipitating aluminum, or no, iron, rather than precipitating out iron, we're going to precipitate out zinc. And so the Zn2 plus, we need 3 of these, plus 2 potassiums. This is called a mixed cation salt. And this mixed cation salt yields this mixed cation precipitate here. I mean, mixed cation mixture leads to mixed cation salt. And so we'll have Zn3K2, it's a zinc potassium salt with the complex FeCN6 there. And we'll need 2 of these. This is a gray-blue precipitate that we have here. All right, that's pretty much the procedure for the flow chart. Now, some of these we're going to analyze individually. So, for example, the sodium we analyze individually. We just get a fresh sample. You only need about 1/2 milliliter to dip. And so we'll get a fresh sample of unknown. The unknown contains all of this, or the known. The ammonium, the same thing. We need a fresh sample of known or unknown. And for the ammonium, we're going to just convert the ammonium into ammonia by just adding base hydroxide here. And so the hydroxide is going to come from sodium hydroxide. And so we're going to add sodium hydroxide to this here. And that converts ammonia into ammonia. Ammonia is very soluble. We'll have water here too. Now we're going to either heat or wait. Heat or wait. This triangle is the symbol for heat. And what happens is the ammonia doesn't stay there, all of it. Some of it kind of bleeds out of solution, that is, degasses out of solution into ammonia gas. Now, ammonia gas is pretty interesting because since it's a gas, we can test just the gas with with red litmus paper here. What we're going to do is we're going to put wet red litmus paper on the bottom of a watch glass. And so as this ammonia gas rises, it comes into contact with the litmus paper and gradually turns it blue. So you should see this thing gradually turn to blue. We don't want to splash any of the liquid on there because the liquid contains strong base hydroxide, but the hydroxide is not going to float up to the litmus. The hydroxide is pretty much stuck here in the aqueous phase, whereas the ammonia can float up to the litmus. And so if we see a gas change red litmus to blue, then that's positive for ammonia, which means we had ammonium in our original unknown. So this is a positive test for ammonium. All right, the next thing we're going to do is we're going to take a look at the anions. The first thing is we're going to look at behavior of anion solids. So we're going to be testing solid samples here with room temperature. It says cold concentrated nitric, but cold being room temperature in this case. And so we have some solids back there. And so we're going to test these separately. So what happens if you add concentrated sulfuric acid? Now you have to watch out for concentrated sulfuric acid. Concentrated sulfuric acid causes severe burns. You could get third-degree burns from spills under your skin. So you got to watch out. So don't touch, avoid contact. if we have sulfate, there's no reaction. If we have nitrate, there's no reaction. If we have carbonate, the carbonate acid converts carbonate into CO2, and so it effervesces. So carbonate, we should see effervescence. With chloride, the sulfuric acid isn't strong enough oxidizer to oxidize the chloride. Instead, what we do is the H plus combines with chloride to produce hydrogen chloride gas. So it has a sharp, pungent odor. Don't breathe in the odor. And don't bother smelling this. It'll cause damage to your mucous membranes. But HCl gas is an acid. And so acids turn blue litmus red. So like ammonia, we could test for this using litmus, and if the gas that hits the litmus turns blue to red, then it's an acidic gas. But are there other acidic gases? We'll see. Now with bromide, sulfuric acid is a strong enough oxidizer, so we're going to use sulfate as the oxidizer. We need H plus to form the water. But basically, the sulfuric acid is going to oxidize bromide to bromine. So bromine is red-brown, and then if you heat this, then it'll form a brown-red gas. You don't want to breathe that. This has got to be done in the hood. HBr is also liberated, which will cause damage to your mucous membrane. We could also oxidize iodide salts. So if we have iodide, a solid salt, we'll oxidize it to iodine. Iodine's purple. So this says it turns dark brown. It's actually purple. It's hard to see the color. Iodine. So those are the solid tests. Then we're going to do other tests, the aqueous tests. And so let's take a look at the aqueous tests here. The most complicated of the aqueous tests is the nitrate test. If you had Chem 4, you've already done a lot of these tests here. But for the nitrate test, we're going to have our sample that contains nitrate. And then to this, we're going to add an equal amount of FeSO4, aqueous. So we should double the volume. And so now we have Fe2 plus and nitrate. And then to this, we're going to tilt this. And then what we're going to do is we're going to carefully add concentrated sulfuric acid. What we need to do is we need to tilt this so that the concentrated sulfuric acid can run down the side of the test tube. So I'd probably tilt this at a more severe angle. Maybe like this. So what I want to happen is I want this sulfuric acid to run down the inside wall. And it's like syrup. It's very viscous. And like syrup, it doesn't dissolve immediately. It takes time for syrup to dissolve in water because you got to break all those strong hydrogen bonding interactions. So sulfuric acid has a lot of strong hydrogen bonding interactions, so it kind of stays together and sinks to the bottom to form a little lake of sulfuric acid solution. Now this is a real lake because this is a liquid. The previous lakes were not real lakes, those were solids, a lake of jello. But here we're going to have the lake of concentrated sulfuric acid. Over time, and if you mix it, it'll mix to be homogeneous, but right now it's heterogeneous. And that's important because we need this little lake of concentrated sulfuric acid at the bottom here. Because what's going to happen is we're going to get a redox reaction. Nitrate is a great oxidizer. So we're going to use the nitrate plus 4H plus 3 electrons to form NO, gas plus 2H2O. And then iron 2 plus is a pretty good reducing agent. Iron 2 plus goes to iron 3 plus, plus an electron. And then we'll multiply this bottom one by 3. And so what we're going to end up with is this. We're going to end up with a nitrate plus 4H plus 3 Fe2 plus yields NO gas plus 2H2O plus 3 Fe3 plus. Now Fe2 plus, this is green, and Fe3 plus is yellow. So this is green, this goes yellow. It's hard to see. And so what we're going to do is we're going to try to detect the presence of NO. But NO is hard to see too. NO is a CCG. So what we're going to do is we're going to let NO be oxidized by air or oxygen. And so we'll take a half an oxygen, and this is going to form NO2. NO2 gas, this is a brown gas. Brown-orange gas. This brown-orange gas is going to form at the interface here. See if I can get a different color here. No, I can't. It doesn't seem to be working. So I'll use green. It's supposed to be brown. And so we're going to get a brown layer of NO2AQ. So we form nitrogen dioxide gas. The nitrogen dioxide gas is going to form right at the interface between the sulfuric acid and our reaction mixture here. The sulfuric acid is important because that's where we get the H plus for a reaction. So the reaction occurs at this interface here. It reacts to form NO, and the NO gets converted into NO2. The NO2 is here. Eventually the brown layer will dissolve into the rest. But right now there's a gradient, concentration gradient, so it's most concentrated here. They call this the brown ring. And so formation of the brown layer, or the brown ring, is positive for nitrate. The test for chloride is easy. Alright, I lost all that earlier stuff. Let's see. Recovered. No. Alright, let me talk about the test for chloride here. If there's chloride present, all we're going to do is add silver nitrate. And then what we're going to get is a white precipitate of silver chloride. In other words, in net ionic form, it's just silver ions plus chloride ions yields silver chloride. Solid. And so this results in a white PPT. Similar to the silver test, except we're adding silver nitrate in this case. Silver nitrate, watch out, it stains everything black. But there's a problem. because there are potential interferences here. And so if we did bromide, we get silver bromide. And so if we had bromide, we get silver bromide, which is an off-white PPT. If we did iodide, we get a yellow precipitate. So these are potential interferences that we could have. So we're going to do some additional tests here. The additional tests would be the same as in Chem 4. And that is, let's do bromide. One way we could tell if we have bromide is by adding chlorine water. So if there's bromide in here and we add chlorine water, that is just chlorine mixed with water, then we're going to get this reaction. That is, 2 bromides plus a chlorine is going to yield 2 chlorides, or no, yeah, 2 chlorides plus a bromine. And so we're going to go from yellow chlorine to red-orange bromine. But the bromine is very difficult to see. And so if we have a bromine in here, if it's dilute, it makes it difficult to see. So what we're going to do is we're going to add 2 drops, 3 drops. It says to add 5 drops, so I think that's overkill. Add 3 drops of mineral oil. The fewer the drops, the more intense the color is going to be. And what's going to happen is oil and water don't mix. And mineral oil is more dense than water. So it forms a little bubble on the bottom. And so what we're going to do is we're going to stopper this. If you use a cork stopper, those are hard to clean. So don't let the liquid splash up onto the cork stopper, otherwise we're going to get cross-contamination. If you have a rubber stopper, this can be hard to clean as well, but either cover the stopper in parafilm. That's what I do. I wrap the stopper in parafilm so I don't have to worry too much about cleaning it. And then shake it. What we want to do when we shake it is we want to get this oil drop to disperse into the liquid and pick up all the bromine. Because bromine prefers to be dissolved in mineral oil than in water. And so what we're going to do is we're going to extract, this is called solvent extraction. So we're extracting the bromine from the water into the mineral oil. And so in solvent extraction, we're extracting the bromine from the water layer to the oil layer. And the reason this works is because bromine is nonpolar and mineral oil is nonpolar. So like dissolves like. Bromine likes mineral oil more than it likes water. And so we can do the solvent extraction, no problem. The advantage of doing the solvent extraction is it makes the color brighter. So this should be bright red, orange. It's just more intense because it's more concentrated, so it's easier to see. All right, then we're going to repeat this with iodide. And when we repeat this with iodide, we're going to form iodine, and the iodine is going to be concentrated in this little bubble. Iodine is purple. Let's see if my colors, yeah, my colors are back. So we'll have a purple layer. And this purple little droplet at the bottom consists of iodine dissolved in mineral oil. Okay, so again, this is solvent extraction. We usually cork it and shake it to disperse the oil into the water so that it picks up the halogen. Finally, we're going to have the carbonate test. Carbonate is usually pretty easy. We take carbonate and then add acid to this. And that's going to form H2O liquid plus CO2 gas. CO2 gas is a CCG, clear colorless gas. So how can we prove that that gas is CO2? Because there's lots of CCGs, like hydrogen gas. One way we can prove it is CO2 is an acid, so it should turn blue litmus red. But CO2 is not acidic enough to do that. And so litmus paper won't work. Ammonia, no problem. Turns red litmus blue. CO2, no. And so we're going to have to take advantage of another chemical property of CO2. And that chemical property is this. We're going to use barium hydroxide. We could use calcium hydroxide too, which works quite well. But we're going to use barium hydroxide. The problem with the barium hydroxide is there's going to be a bunch of white precipitate in there. If there's a bunch of precipitate in there, that precipitate is contamination. And barium hydroxide typically is contaminated with barium carbonate. We don't want that contamination. So what we're going to do is we're going to centrifuge so that it puts the precipitate on the bottom here. So this is the barium carbonate. And now we have the barium hydroxide on the top. And then we're going to get a little dropper pipette and put that in here. So this should be a CCS. Normally it's cloudy with contamination. And the reason it gets cloudy with contamination is because of this. When we suspend this drop, we're going to suspend a half a drop of barium hydroxide on here. And then we're going to let the CO2 gas rise up and come in contact with that. As the CO2 gas rises up and comes in contact, we start to form a crusty layer on the surface. And that crusty layer is a precipitate. It's a white layer. And so the CO2 plus the barium hydroxide forms barium carbonate, which is a precipitate, and two hydroxides. Or no, H2O, sorry. Okay, this is the layer, the crusty layer that forms on the drop. And so this would be barium carbonate precipitate on the surface. And so we're going to test the gas for CO2. If there's CO2, we expect to form a white crust on there. All right, any questions on this? No? All right, we'll stop here and then you can take a break, or you can go ahead and get started. On lab.